In modern cosmology, there is a disturbing implication hidden inside thermodynamics and infinity. If the universe lasts forever, random quantum fluctuations could eventually arrange particles into a self-aware human brain floating in empty space, complete with memories and consciousness. These hypothetical entities are called Boltzmann brains, named after physicist Ludwig Boltzmann. Statistically, in an eternal universe, such random observers could outnumber naturally evolved humans. The terrifying consequence is philosophical as much as scientific. A Boltzmann brain could remember a childhood, history, even reading this sentence, despite none of it ever happening. Its entire reality would be an illusion created by chance. If cosmological theories predict more Boltzmann brains than real observers, then probability suggests we ourselves are more likely to be one of these temporary, hallucinating minds. For some physicists, that possibility is so absurd that any valid theory of the universe must somehow prevent it. The thermodynamic arrow and why it points only one way. The second law of thermodynamics is the most asymmetric statement in all of physics. Every other fundamental law, from Newton's mechanics to Maxwell's electromagnetism to the Schrödinger equation, is time-symmetric. Run the equations forward or backward, and they remain valid. A film of two billiard balls colliding is physically indistinguishable whether played forward or in reverse. But a film of an egg falling off a table and shattering into pieces becomes immediately, obviously absurd when reversed. The shards do not leap off the floor, assemble themselves into an egg and jump back onto the counter. This asymmetry is what physicists mean by the thermodynamic arrow of time, and its origin is one of the deepest and most consequential puzzles in the history of science. The formal statement of the second law is that the total entropy of an isolated system never decreases over time. Entropy, in the statistical mechanics framework developed by Ludwig Boltzmann in the 1870s and 1880s, is a measure of the number of microscopic configurations, called microstates, that are consistent with the observable macroscopic state of a system. A gas compressed into one corner of a box has low entropy because there are relatively few ways to arrange all its molecules while keeping them in that corner. A gas spread uniformly throughout the box has high entropy because there are astronomically more arrangements consistent with that uniform distribution. The reason gases expand to fill their containers is not because of any directed force pushing them outward. It is because the overwhelming majority of possible microstates are spread out states, and a system evolving randomly through its available microstates will, with near certainty, find itself in a high entropy configuration. This is Boltzmann's great insight, and it remains the foundation of our understanding of irreversibility. Entropy increase is not a law in the same sense as conservation of momentum. It is a statistical near certainty so overwhelming that it functions as a law for all practical purposes. The probability that all the molecules in a 1 liter container of air would spontaneously collect into 1/2 of the container is not zero, but it is so vanishingly small that waiting the entire current age of the universe repeated an unimaginable number of times would not meaningfully increase your chances of observing it. The number of microstates corresponding to the low entropy configuration is so vastly smaller than the number corresponding to high entropy configurations that the ratio is effectively zero for any system of macroscopic size. The critical point here is that the second law does not explain why entropy is low right now. It explains why entropy will be higher in the future than it is at present. But for the law to make contact with our experience, one additional assumption is required. The entropy of the universe was very low in the past. This assumption, sometimes called the past hypothesis, is not derived from any dynamical law. It is an initial condition imposed by hand whose ultimate origin is not understood. The universe we observe emerged from the Big Bang in an extraordinarily low entropy state. The cosmic microwave background, measured with exquisite precision by the Wilkinson Microwave Anisotropy Probe, beginning in 2001 and later by the Planck satellite, shows a universe that was almost perfectly uniform in temperature to 1 part in 100,000 shortly after the Big Bang. That uniformity, combined with the smooth and unclustered distribution of matter at early times, represents an entropy vastly lower than the entropy of the universe today, with its galaxies, stars, black holes, and complex structures. Why was the early universe in such a low entropy state? This question has no currently accepted answer within physics. The inflationary cosmology developed by Alan Guth in 1980 and refined by André Linde, Paul Steinhardt and others addresses the uniformity problem from a different angle, proposing that a period of exponential expansion in the very early universe would smooth out any initial irregularities. But inflation does not eliminate the need for a low entropy initial condition. It arguably transfers the problem to the pre-inflationary state, which must itself have been specially arranged to initiate inflation. Sean Carroll and Jennifer Chen argued in a 2004 paper in Physical Review Letters that inflation makes the problem worse rather than better, because the conditions required to start inflation are themselves extraordinarily improbable from a statistical standpoint. The thermodynamic arrow therefore rests on a foundation that is not fully understood. We know entropy increases because low entropy states evolve into high entropy states with overwhelming probability. We know the universe currently has relatively low entropy because it began in an even lower entropy state. But we do not know why it began that way. This gap in our understanding is not merely an academic inconvenience, it is the opening through which one of the most unsettling ideas in the history of physics enters. If we take Boltzmann's statistical reasoning seriously and apply it not just to gases in boxes, but to the entire universe across all of time, the consequences are deeply disturbing. They lead, by a chain of logic that is difficult to break, to the possibility that the most common kind of conscious observer in any sufficiently old and large universe is not a creature who evolved through billions of years of natural selection, embedded in a coherent physical world, but rather a disembodied mind that assembled itself from a random fluctuation in the void. Understanding how we get there requires first understanding what Boltzmann himself thought about the nature of time and the crisis that his own reasoning eventually created. Boltzmann's original crisis and the statistical mechanics of despair. Ludwig Boltzmann's intellectual life was defined by a single enormous ambition and a single devastating objection to it. The ambition was to reduce the second law of thermodynamics to a consequence of Newtonian mechanics applied to atoms, thereby explaining irreversibility from the ground up. The devastating objection came from his colleagues, most prominently Joseph Loschmidt and Ernst Zermelo, and it struck at something so fundamental that Boltzmann spent the last 2 decades of his life struggling to answer it. The struggle led him, in his later papers and lectures, to contemplate the structure of the universe on the largest possible scales, and in doing so, to accidentally plant the seed of the Boltzmann brain problem. Boltzmann's H theorem of 1872 appeared to demonstrate that a gas of molecules obeying Newtonian mechanics would inevitably evolve toward higher entropy, as measured by his H function. But Loschmidt raised a crippling objection in 1876, now known as the reversibility objection, or Loschmidt's paradox. If the underlying equations of Newtonian mechanics are time-symmetric, then for every trajectory along which entropy increases, there exists an equally valid time-reverse trajectory along which entropy decreases. The equations do not prefer one direction of time over the other. Any statistical argument that entropy must increase should apply equally well to the time-reverse case and predict that entropy can decrease, which contradicts the conclusion of the H theorem. Boltzmann's proof of irreversibility therefore had to contain a hidden asymmetric assumption, and when examined carefully, it did. The so-called Stochalansatz, or molecular chaos assumption, which effectively assumed the absence of correlations between colliding molecules. This assumption is itself time asymmetric. Boltzmann's response to the reversibility objection was to reframe the second law as a statistical statement rather than an absolute one. Entropy increase is not guaranteed by the dynamics. It is overwhelmingly probable. In a large system with many degrees of freedom, the fraction of microstates in which entropy would decrease over any given time interval is so small as to be negligible. The system spends its time wandering through microstates, and the overwhelming majority of those microstates are high entropy states. If you find the system in a low entropy state, it almost certainly arrived there from an even lower entropy state in the past, and it will almost certainly evolve toward a higher entropy state in the future. Then in 1896 came a second, even sharper objection. Henri Poincaré had proved in 1890 that any mechanical system with finite energy confined to a finite volume will, given sufficient time, return arbitrarily close to any initial configuration. This is the Poincaré recurrence theorem. Zermelo used this theorem to construct a new paradox. If a gas that has spread to fill a container will eventually return to its compressed initial state, then entropy cannot simply and monotonically increase. The system must decrease in entropy during its return to the initial configuration. A thermodynamic theory that predicts monotonic entropy increase is therefore inconsistent with Newtonian mechanics. Boltzmann's response to the recurrence objection was subtle and, in retrospect, cosmologically profound. He argued that, yes, any finite system will indeed recur, and entropy will sometimes fluctuate downward. But the time required for a Poincare recurrence is so astronomically large, far exceeding the current age of the universe even for systems of modest size, that the second law is not practically violated. A mole of gas at room temperature would require a recurrence time roughly on the order of 10 to the power of 10 to the power of 23 seconds to spontaneously return to a compressed configuration. This number is so large it has no meaningful analogue in physical reality. The universe is approximately 4.3 times 10 to the 17 seconds old. The recurrence time for a macroscopic gas exceeds this by so many orders of magnitude that entropy increase is, for any observable purpose, universal. But here, Boltzmann was forced into a further argument that carried extraordinary implications. If the universe is itself a finite system in thermal equilibrium, as some physicists of his era believed, then its current low entropy state must itself be understood as a fluctuation. A universe in true thermal equilibrium, the state of maximum entropy, would be a featureless uniform distribution of matter and energy at a single temperature. Such a universe would be lifeless, structureless, and eternal. Within that eternal equilibrium, however, statistical fluctuations would occasionally produce temporary reductions in entropy. Most fluctuations would be tiny, a few molecules momentarily clustering together. Larger fluctuations would be exponentially rarer, and a fluctuation large enough to produce a galaxy, a star, a solar system, and the entire observable universe would be so rare as to be almost unthinkable. But given infinite time, it would eventually occur. This is the context in which Boltzmann, in an 1895 paper published in Nature and in later work with his student Ignaz Schwarz, proposed what is now sometimes called the Boltzmann universe hypothesis. Perhaps our universe, with all its low entropy structure, is itself one of these rare fluctuations in an otherwise equilibrium cosmos. The low entropy we observe around us is not the result of special initial conditions imposed at the Big Bang. It is a temporary departure from equilibrium, statistically inevitable over an infinite timescale that happen to produce conditions hospitable to life and consciousness. The immediate problem with this proposal, and the one that Boltzmann himself recognized and agonized over, is that it wildly overestimates the required fluctuation. If the universe is a fluctuation, the fluctuation should be only as large as necessary to produce the observers who are actually experiencing it. A fluctuation large enough to produce the entire observable universe, with its 2 times 10 to the 23 stars, its billions of galaxies, and its vast stretches of ordered space-time is enormously more improbable than a fluctuation large enough to produce just one planet with one observer. A fluctuation large enough to produce just one observer with genuine memories and sensory organs is more improbable still than a fluctuation large enough to produce just the bare minimum required for a conscious experience. A brain, with its attendant sensory data and memories, spontaneously assembled by a random thermal fluctuation, of these minimal observers fluctuating briefly into existence in an otherwise featureless thermal bath, are what later physicists would come to call Boltzmann brains. Boltzmann himself came close to this conclusion, but did not state it in quite this form. He died in 1906, before the concept was made fully explicit, and before the cosmological framework existed that would eventually make the problem acutely dangerous to modern physics: what a fluctuation actually is at cosmological scales. The word fluctuation in the context of thermodynamics has a precise meaning that becomes increasingly alarming when extended to cosmological scales. A thermal fluctuation is a spontaneous temporary departure from the equilibrium configuration of a system, driven by the random motion of its constituent parts. In everyday statistical mechanics, fluctuations are small and brief. The density of air in a room fluctuates slightly from point to point because the molecules are not perfectly uniformly distributed. These fluctuations are on the order of 1 part in the square root of the number of molecules in the volume being considered, which for any macroscopic volume is negligibly small. But the laws of statistical mechanics do not place an upper limit on the size of fluctuations. They only assign probabilities. Any fluctuation, no matter how large, has a non-zero probability of occurring in a sufficiently old system. The probability of a fluctuation is determined by the entropy difference between the fluctuated state and the equilibrium state. Boltzmann's equation, engraved on his tombstone in Vienna, states that the entropy S of a system equals Boltzmann's constant key multiplied by the natural logarithm of the number of microstates W corresponding to that configuration. S equals K times the natural log of W. Equivalently, the probability of spontaneously observing a configuration with entropy S in a system at equilibrium is proportional to e to the power of S divided by K, or equivalently, to e to the power of W. This means that fluctuations become exponentially less probable as their entropy decreases relative to the equilibrium value. A fluctuation that decreases entropy by an amount delta S has probability proportional to e to the negative delta S divided by K. For delta S values corresponding to macroscopic objects, this probability is so small that even writing it in standard scientific notation is cumbersome. To appreciate the scale of the problem, consider what is required to spontaneously assemble a human brain from the particles in a thermal bath. A human brain contains approximately 1.5 kilograms of matter, organized into roughly 86 billion neurons, with on the order of 100 trillion synaptic connections. The information content required to specify the precise arrangement of atoms in a functioning brain is enormous. The entropy difference between a functioning brain and the same mass of matter distributed randomly at thermal equilibrium is not precisely known, but dimensional analysis and order of magnitude estimates place it at something like 10 to the 25 joules per Kelvin or larger. The probability of such a fluctuation occurring in a gas at room temperature over a volume of, say, 1 cubic meter in 1 second is proportional to e to the negative 10 to the 25, which is a number so close to zero that it has no analogue in observable physics. The number of protons in the observable universe is approximately 10 to the 80. The probability of a brain fluctuation is suppressed relative to even this minuscule baseline by a factor that makes it, in any practical sense, impossible. But impossible and zero probability are not the same thing. Given sufficient time and a sufficiently large system, a brain fluctuation becomes inevitable. The question is whether the universe is, or will ever be, old enough and large enough for such fluctuations to matter. In Boltzmann's era, this was an abstract question. In the context of modern cosmology, particularly with the discovery of the accelerating expansion of the universe and the associated positive cosmological constant, it is no longer abstract at all. A universe dominated by a positive cosmological constant, like the one we appear to inhabit, does not simply expand and cool to absolute zero. Instead, it approaches an asymptotic state called de Sitter space, named for the Dutch astronomer Willem de Sitter, who found this solution to Einstein's field equations in 1917. De Sitter space is not a cold, empty, dead universe. It is a universe with a non-zero temperature, called the Gibbons-Hawking temperature, arising from quantum effects associated with the cosmological event horizon. Gary Gibbons and Stephen Hawking derived this result in a 1977 paper in Physical Review D. The Gibbons-Hawking temperature of the de Sitter space corresponding to our observed cosmological constant is approximately 2.3 times 10 to the negative 30 Kelvin, which is extraordinarily cold but not zero. A universe at non-zero temperature is a universe in a thermal state. A universe in a thermal state undergoes thermal fluctuations. A universe that remains in a thermal state for an infinite amount of time will, by the logic of statistical mechanics, eventually produce every possible fluctuation, including fluctuations that spontaneously assemble brains, memories, sensory experiences, and every other conceivable configuration of matter. The timescale required for a brain fluctuation to occur, even once in the observable universe, is vastly larger than the Poincaré recurrence time for a macroscopic gas. Estimates suggest something on the order of e to the power of 10 to the 66 years for a simple quantum fluctuation of the required complexity, though the exact number depends sensitively on what exactly constitutes the minimal observer. But these timescales, however vast, are finite, and if de Sitter space is eternal, or even if it persists for times much larger than these recurrence timescales, then Boltzmann brains are not only possible, they are inevitable, and they are extraordinarily numerous. The distribution of fluctuations in an eternally hot de Sitter universe is not uniform in complexity. Small fluctuations are vastly more common than large ones. A fluctuation that produces a single organized particle is more common than one that produces a complex molecule. A fluctuation that produces a minimal observer, the smallest possible self-consistent conscious entity, is vastly more common than a fluctuation that produces a full human being with a body. An evolutionary history and an accurate memory of a coherent external world. Fluctuation cosmologists must therefore grapple with a conclusion that seems unavoidable. If our universe is eternal and thermally active, then the dominant type of observer in it, measured by sheer number, is not a being like us, who evolved through natural selection in a coherent physical environment, but a minimal conscious fluctuation, a Boltzmann brain, the brain that assembles from nothing. The Boltzmann brain, as a concept in modern cosmology, was given its contemporary form in papers by Andreas Albrecht and Lorenzo Sorbo in 2004, and by Don Page in a series of influential papers beginning in 2006, though the lineage traces directly back to Boltzmann's own cosmological speculations. The central claim is straightforward even if its implications are not. In any universe that remains in a state of non-zero temperature for a sufficiently long time, statistical fluctuations will eventually assemble every possible physical configuration, including configurations that constitute functioning, experiencing minds. These minds, assembled from the random churning of a thermal bath, would experience themselves as coherent observers, would have what appear to be memories and sensory perceptions. But those memories and perceptions would not correspond to any genuine external reality. They would be artifacts of the fluctuation itself. The key distinction between a Boltzmann brain and an evolved observer like a human being is the causal history. A human being's sensory organs, neural architecture, and memories were produced by a long chain of causal processes, biological evolution over hundreds of millions of years, individual development over decades, a continuous stream of sensory experience that shaped the brain's structure. The information encoded in a human brain about the external world is causally connected to that world. When you remember that the sky is blue, this memory traces back through a chain of causes to actual photons reflecting off actual molecules in the atmosphere and entering your actual eyes. The correspondence between your mental states and the external world is not coincidental. It is the product of reliable causal processes operating over long timescales. A Boltzmann brain has no such causal history. It assembles in an instant from a random fluctuation. Whatever memories it appears to have are not the product of genuine past experiences, but are instead configurations of matter that happen by chance to resemble the brain states that would result from genuine experiences. The Boltzmann brain might appear to remember a childhood, a career, relationships with other people, the reading of physics textbooks. But none of these apparent memories correspond to actual events. They are noise that happens by an extraordinary coincidence, to be structured like signal. This is not a merely philosophical point, it has direct physical implications for what such an observer would experience. A Boltzmann brain, assembled in an otherwise featureless thermal equilibrium, would exist for only a brief moment before being destroyed by the same thermal processes that created it. Its sensory experience, if it has any, would be radically incoherent. It would appear to be immersed in a thermal bath at the Gibbons-Hawking temperature of de Sitter space, which is nothing like the structured, lawful, coherent world that evolved observers like humans perceive. The brain's apparent memories of a lawful, structured world would be immediately contradicted by its actual sensory environment, to whatever extent it can be said to have sensory experience at all. Andreas Albrecht's 2004 paper in Physical Review Letters with Lorenzo Sorbo laid out the problem with particular clarity in the context of inflationary cosmology. They pointed out that the standard argument for why the early universe was in a low entropy state, namely that inflation drove it there, runs into a catastrophic problem when you consider the full population of observers in an eternally inflating multiverse. Inflation produces vast numbers of universes, most of which are in high entropy states. Within each universe, including our own, the long-term future involves a de Sitter phase with Gibbons-Hawking temperature, and this de Sitter phase produces Boltzmann brains at an enormous rate compared to the rate at which normal observers arise through biological evolution. Over sufficiently long timescales, the ratio of Boltzmann brains to ordinary observers becomes astronomical. Don Page, in his 2006 paper, The Lifetime of the Universe, and subsequent work, attempted to quantify this ratio more carefully. For a universe with the cosmological constant, we observe approximately 1.1 times 10 to the negative 52 per square metre, and assuming the universe lasts indefinitely in a de Sitter phase, the number of Boltzmann brains produced over all future time vastly exceeds the number of ordinary observers who arose through biological evolution during the brief matter-dominated and radiation-dominated eras. The ratio depends sensitively on the assumed lifetime of the de Sitter phase and on what exactly constitutes the minimal observer. But under plausible assumptions, Boltzmann brains outnumber ordinary observers by a factor that grows without bound as the future time considered grows. In the infinite limit, essentially all observers are Boltzmann brains. The precise mechanism by which a Boltzmann brain would form in de Sitter space is not fully specified, because we do not have a complete quantum theory of gravity. But several mechanisms have been proposed. One involves quantum tunneling. The vacuum of de Sitter space is not completely stable at the quantum level, and quantum tunneling processes can nucleate bubbles of matter in configurations far from thermal equilibrium, including configurations that constitute organized physical structures. Another involves thermal fluctuations in the semi-classical picture. The Gibbons-Hawking temperature represents real photons and particles being produced near the cosmological horizon, and in principle, these particles can be in any quantum state, including highly organized states. A third possibility, discussed by Sean Carroll and others, is that Boltzmann brains arise through quantum fluctuations of the vacuum itself, without requiring the production of classical particles at all. The disturbing aspect of the Boltzmann brain is not primarily its exotic origin. It is the question of whether you might be one. If Boltzmann brains vastly outnumber ordinary observers in the universe, then any randomly selected observer is overwhelmingly more likely to be a Boltzmann brain than an evolved being. You consider yourself an evolved observer with genuine memories of a coherent past and genuine sensory access to a lawful external world. But if the logic of statistical mechanics applied to cosmology is correct, and if the universe is in or approaching a long-lived de Sitter phase, then the prior probability of being the kind of observer you think you are is essentially zero, because almost no observers are of that type. Almost all observers are minimal fluctuations with false memories and incoherent perceptions. The theory that gives you the most tools to understand the world simultaneously provides strong statistical reason to doubt that your understanding of the world is based on anything real. Why Boltzmann brains outnumber real observers by an astronomical factor. The quantitative argument for the dominance of Boltzmann brains over evolved observers requires putting concrete numbers to the rate at which each type of observer is produced in a universe like ours. This is genuinely difficult because it requires estimates of both the total number of evolved observers that will ever exist and the total number of Boltzmann brain fluctuations that will occur over all of cosmic time. Both estimates are uncertain, but the qualitative conclusion that Boltzmann brains overwhelmingly dominate is robust across a wide range of assumptions. Consider first the production of evolved observers. Intelligent life in our universe requires stars to produce heavy elements, planets in stable orbits, liquid water, chemistry capable of replication and evolution, and billions of years of continuous habitability. The window during which these conditions are met in our universe is roughly the Stelliferous era, which runs from approximately 10 million years after the Big Bang to approximately 100 trillion years in the future, when the last low-mass red dwarf stars exhaust their hydrogen. The number of stars that will ever exist in the observable universe is estimated at somewhere between 10 to the 23 and the 10 to the 24. If even a small fraction of these stars host planets with intelligent observers, the total number of evolved observer moments, a unit commonly used in this context to count each moment of conscious experience as one unit over the entire Stelliferous era, is very large, perhaps 10 to the 100 or more. This is an enormous number by everyday standards. Now consider the production of Boltzmann brains in the subsequent de Sitter era. After the last stars burn out and the universe enters its de Sitter phase, the Gibbons-Hawking temperature ensures a continuous thermal bath. The rate at which a fluctuation of a given complexity occurs is determined by the Boltzmann suppression factor E to the negative delta S over K, where delta S is the entropy decrease required. For a minimal observer, the simplest possible self-consistent brain, delta S is smaller than for a full human brain, making such a fluctuation more probable. The rate of production of minimal Boltzmann brains per unit volume per unit time is approximately e to the negative 10 to the 25 per cubic meter per second, using rough estimates of the minimum entropy decrease required. This rate is unimaginably small. Per any observable volume, the expected waiting time for one such fluctuation is many orders of magnitude longer than the current age of the universe. But here is where the comparison becomes decisive. The de Sitter era is not brief. It does not last for a few trillion years. It lasts forever, or at least for a time that is effectively infinite compared to the Stelliferous era. The cosmological constant we observe shows no sign of decaying. If it is truly constant, the universe will remain in a de Sitter phase for eternity. and an eternal de Sitter space, however slowly it produces Boltzmann brains, will produce infinitely many of them. The ratio of Boltzmann brain observer moments to evolved observer moments is then infinite divided by finite, which is infinite. Every cosmological scenario in which the de Sitter phase lasts significantly longer than the recurrence time for a minimal observer results in Boltzmann brains dominating the observer population by a factor that is, in the relevant limit, unbounded. Kim and Page in a 2007 paper, and Garriga, Guth, and Vilenkin in related work examined various measures for counting observers and found that the conclusion is not sensitive to the specific counting scheme. Whether you count individual observer moments, distinct observers, or some other unit, and whether you use a co-moving volume cutoff, a proper time cutoff, or various other regularization schemes designed to handle the infinities that arise in eternal cosmologies, Boltzmann brains dominate unless you impose specific physical mechanisms that either decay the de Sitter vacuum on a timescale shorter than the Boltzmann brain recurrence time, or otherwise suppress the formation of Boltzmann brains. The problem is made worse by the observation that smaller fluctuations are more common than larger ones. A Boltzmann brain that consists of the minimum possible amount of organized matter needed to support conscious experience is more probable than one that has a full human body. A Boltzmann brain with the minimum sensory input needed to constitute an experience is more probable than one with fully functional eyes, ears, and other organs. This means the dominant Boltzmann brains in the distribution are not coherent beings. They are the absolute minimum, instantaneous flashes of experience appearing in a thermal bath, without bodies, without continuous sensory input, without any stable embedding in a physical environment. The most common observers in an eternal de Sitter universe are observers experiencing pure noise, momentarily coalesced from the quantum vacuum, experiencing nothing that corresponds to the ordered, lawful, predictable world that you believe you are experiencing right now. The Stelliferous era, during which evolved observers like humans exist, is approximately 10 to the 14 years long. The Boltzmann brain recurrence time for a minimal observer in de Sitter space is roughly e to the 10 to the 66 years, an incomprehensible number, but a finite one. After this recurrence time has elapsed, the expected number of Boltzmann brain observer moments in the de Sitter phase equals roughly the number of evolved observer moments in the Stelliferous era. After twice the recurrence time, Boltzmann brains are already dominant. The universe then continues, in principle, for infinite time, producing Boltzmann brains at the same tiny but non-zero rate forever. The ratio of Boltzmann brains to evolved observers grows without bound as time goes on. There is no obvious way out of this conclusion that does not require either a modification of our cosmological model or a modification of our understanding of what it means to count observers. The observed cosmological constant appears stable. The Gibbons-Hawking temperature of de Sitter space is a robust prediction of semi-classical quantum gravity, confirmed by multiple independent derivations. The statistical mechanics argument that a non-zero temperature system will eventually fluctuate into any accessible configuration is among the most solid results in all of physics. The conclusion that Boltzmann brains dominate the observer population in our universe appears to follow from premises that are very well established, and this is precisely what makes it so threatening. The multiverse makes the problem catastrophically worse. If the Boltzmann brain problem is already severe in a single universe with a positive cosmological constant, the addition of a multiverse, specifically the eternally inflating multiverse that arises naturally from most versions of inflationary cosmology, makes it dramatically worse. The problem metastasizes from a concern about the long-term future of our universe to a structural feature of almost every cosmological model that physicists currently take seriously. Eternal inflation was first proposed by Alexander Vilenkin in 1983 and developed independently by André Linde in his chaotic inflation scenario of the same year. The basic mechanism is that in many inflationary models, quantum fluctuations during the inflationary phase cause some regions of space to continue inflating even as others slow down and reheat to produce universes like ours. The inflating regions expand exponentially fast, and because the rate of inflation exceeds the rate at which inflation terminates, the total volume of space that is still inflating grows without bound. Inflation, once started, never completely stops. It produces an infinite number of bubble universes, each of which is a separate region of space that has stopped inflating and evolved into something resembling our universe, but potentially with different physical constants, different symmetry breaking patterns, and different low-energy physics. Within this framework, our observable universe is one bubble among an infinite, eternally growing number of bubbles. Each bubble universe, after its inflationary phase ends, passes through radiation domination, matter domination, and if it has a positive cosmological constant, eventually enters a de Sitter phase. Each bubble universe's de Sitter phase produces Boltzmann brains. And because there are infinitely many bubble universes, the total production of Boltzmann brains is not merely infinite in the future of a single universe, it is infinite in the current snapshot of the eternally inflating multiverse, distributed across the infinite ensemble of bubble universes. The measure problem is the central mathematical difficulty introduced by eternal inflation. In an infinite space containing infinitely many observers of both the evolved and Boltzmann brain varieties, probabilities are not well defined without a prescription for how to compare different infinite sets of events. This is the cosmological version of the problem of picking a random integer. Any finite integer you pick has probability 0 of being the largest, but the distribution over all integers is not normalizable, and so probabilities cannot be straightforwardly assigned. Various measure prescriptions have been proposed to handle this: the proper time cutoff, the scale factor cutoff, the causal patch measure, the co-moving volume measure, and others. Each gives different predictions for the relative probability of being an evolved observer versus a Boltzmann brain. Some of these measures strongly suppress Boltzmann brains, others do not. The problem is that there is no consensus on which measure is correct, and the choice of measure has enormous implications for whether the theory we are using to describe cosmology is self-consistent. Andrei Linde and Vitaly Vanchurin examined the Boltzmann brain problem in eternal inflation in a 2010 paper in Physical Review D. They found that under the simplest measure prescription, the population of Boltzmann brains dominates overwhelmingly over the population of normal observers. The ratio is not a factor of a few, or even a factor of 10 to the 100. It is a factor that grows exponentially with the ratio of the de Sitter recurrence time to the stelliferous era. For physically reasonable parameters, this factor is so enormous that calling Boltzmann brains more common than evolved observers understates the case by an unimaginable margin. Linde and collaborators refer to this as the Boltzmann brain catastrophe. The scale factor cutoff measure advocated by de Simone, Guth, Lim, Salem, and Schwarz-Perloff in a series of papers from 2008 to 2010 was partly designed to suppress Boltzmann brain production relative to normal observer production. Under this measure, events are weighted by the exponential expansion factor of the universe at the time they occur, which strongly downweights events that occur in the far future of a de Sitter phase. This effectively eliminates Boltzmann brains from the dominant contribution to the observer population. But the scale factor cutoff is not derived from first principles. It is chosen partly because it gives reasonable answers, which raises the concern that it is being chosen to avoid the Boltzmann brain problem rather than because there is an independent physical reason to prefer it. The causal patch measure associated with work by Raphael Busseau and collaborators including Busseau and Polchinski's 2004 paper in the Journal of High Energy Physics considers only the region of space-time accessible from a single observer's world line. Within the causal patch, The de Sitter phase has a finite lifetime from the perspective of any given observer's causal horizon, which limits the number of Boltzmann brain fluctuations that can be observed. This measure also suppresses Boltzmann brains, but has its own difficulties, including sensitivity to the initial conditions of the causal patch and complications when applied to eternal inflation, de Sitter space, and the vacuum that never cools. The physics of de Sitter space occupies a central role in the Boltzmann brain problem, and it deserves careful examination beyond the brief treatment in earlier chapters. De Sitter space is the maximally symmetric solution to Einstein's field equations in the presence of a positive cosmological constant. It was discovered by Willem de Sitter in 1917, just 2 years after Einstein published the field equations, and for much of the 20th century, it was regarded as a mathematical curiosity rather than a physically relevant space-time. The discovery in 1998 that the expansion of the universe is accelerating, published by the High Z supernova search team, led by Brian Schmidt and Adam Rees, and independently by the Supernova Cosmology Project, led by Saul Perlmutter, changed this assessment completely. Both teams used Type Ia supernovae as standard candles to measure the expansion rate at cosmological distances, and both found that distant supernovae are fainter than expected, indicating that the universe is expanding faster today than it was in the past. The most straightforward explanation is a positive cosmological constant, which behaves as a source of energy density that remains constant as space expands, causing the expansion rate to accelerate over time. For this discovery, Rees, Perlmutter and Schmidt were awarded the Nobel Prize in Physics in 2011. In a universe dominated by a positive cosmological constant, every region of space asymptotically approaches the geometry of de Sitter space as matter and radiation are diluted by expansion. The characteristic length scale of de Sitter space is the de Sitter radius, defined as the square root of 3 divided by the cosmological constant, which for our observed cosmological constant of approximately 1.1 times 10 to the negative 52 per square meter is approximately 1.6 times 10 to the 26 meters, close to the current Hubble radius of the observable universe. Any 2 points in de Sitter space that are separated by more than this distance are causally disconnected. Light signals sent between them can never arrive, because the space between them is expanding faster than the speed of light. This causal structure gives de Sitter space its distinctive thermodynamic properties. In 1977, Gary Gibbons and Stephen Hawking published a foundational paper in Physical Review D, demonstrating that an observer in de Sitter space perceives the vacuum state as a thermal bath of radiation at a temperature T equals h bar times c divided by 2pi times k times L, where L is the de Sitter radius, h bar is the reduced Planck constant, c is the speed of light, and k is Boltzmann's constant. Substituting our observed values gives a temperature of approximately 2.3 times 10 to the negative 30 Kelvin. This is the Gibbons-Hawking temperature, and it is not merely a formal analogy to the Hawking temperature of black holes. It represents real physical radiation. The quantum vacuum fluctuations of fields in de Sitter space produce real particles near the cosmological horizon, analogous to the way quantum vacuum fluctuations near a black hole's event horizon produce Hawking radiation. The origin of the Gibbons-Hawking temperature lies in the relationship between the thermodynamics of horizons and quantum field theory in curved spacetime. When a quantum field is quantized in de Sitter space, the modes of the field that are inside the observer's causal horizon are entangled with modes outside it. The observer has no access to the modes outside the horizon, which means that from the observer's perspective, the quantum state of the field inside the horizon is a mixed state, described by a density matrix obtained by tracing over the inaccessible modes. This density matrix has the form of a thermal state at the Gibbons-Hawking temperature. The result is exact in the de Sitter background and is robust against small perturbations, meaning it is not an artifact of idealized geometry. The critical point for the Boltzmann brain problem is that this temperature, however small, is non-zero. A spacetime at non-zero temperature is a spacetime in which particles and energy are continuously being produced and destroyed by quantum fluctuations. The production rate of particles with mass m and temperature T is suppressed by the Boltzmann factor E to the negative mc squared over kT. But for sufficiently small masses or sufficiently high temperatures, particle production is significant. For our de-Sitter temperature of 2.3 times 10 to the negative 30 Kelvin, even a single electron with rest mass energy of 511 kiloelectron volts is suppressed by a factor of E to the negative 10 to the 40, making electron production extraordinarily rare. But over infinite time, this production is still guaranteed. The thermal nature of de Sitter space also has implications for the stability of the vacuum itself. In quantum field theory, the vacuum is not a simple empty state, but a complex structure defined by the quantum numbers of all the fields present. Different vacuum states can have different energies, and quantum tunneling can cause the vacuum to transition from a higher energy metastable state, a false vacuum, to a lower energy state, the true vacuum. In de Sitter space, the Gibbons-Hawking temperature provides thermal energy that can assist such tunneling processes. Callan and Coleman in 1977 calculated the rate of vacuum decay through quantum tunneling. In de Sitter space, the Gibbons-Hawking temperature adds a thermal component to this rate that can be significant if the tunneling barrier is low enough. This vacuum instability is directly relevant to whether our universe will remain in a de Sitter phase forever. If the current cosmological constant corresponds to a metastable vacuum, the universe will eventually tunnel to a different vacuum state, potentially with a different or even zero cosmological constant. If such tunneling occurs on a timescale shorter than the Boltzmann brain recurrence time, it might solve the Boltzmann brain problem by terminating the de Sitter phase before significant numbers of Boltzmann brains can form. But this resolution requires knowing the full landscape of vacuum states in the underlying theory of quantum gravity, which is not currently known, and it requires the tunneling rate to fall within a very specific range. If tunneling is too fast, the universe is unstable and inconsistent with observations. If tunneling is too slow, Boltzmann brains dominate. Getting the rate right requires fine-tuning that is no less problematic than the original cosmological constant problem. The Gibbons-Hawking temperature of de Sitter space is, in a very precise sense, the engine that drives the Boltzmann brain problem in modern cosmology. Every argument for why Boltzmann brains are produced at some non-zero rate in our universe traces back to the fact that our universe asymptotes to a space-time with a non-zero temperature, and that a space-time at non-zero temperature is a space-time that continuously fluctuates. The problem cannot be dissolved by simply pointing to how cold de Sitter space is. Coldness delays, but does not prevent the production of fluctuations. Given infinite time, a thermal bath at 10 to the negative 30 Kelvin is just as deadly to the epistemic foundations of physics as one at room temperature. The only escape is to argue that the de Sitter phase does not in fact last forever. The horizon problem and thermal radiation in empty space. The thermodynamic properties of event horizons are among the most profound discoveries of 20th century theoretical physics, and their implications extend far beyond the black hole context in which they were first understood. The Gibbons-Hawking temperature of de Sitter space is one instance of a general principle. Whenever a quantum observer has access to only a portion of the quantum state of a field, because the rest of the field is hidden behind an event horizon, that observer perceives the vacuum as a thermal state. This principle, which connects general relativity, quantum mechanics, and thermodynamics in a deep and not fully understood way, is at the heart of why empty space is not truly empty in the cosmological context relevant to Boltzmann brains. The first hint of this connection came from Jacob Bekenstein's 1972 and 1973 papers, proposing that black holes carry entropy proportional to the area of their event horizons. Before Bekenstein's work, the possibility that a black hole could have a temperature or entropy seemed paradoxical. Classical general relativity predicts that nothing can escape from a black hole, so it seemed impossible for a black hole to radiate or to have a temperature in any thermodynamically meaningful sense. Bekenstein's argument was based on the observation that the area of a black hole's event horizon never decreases under classical evolution, in direct analogy with the second law of thermodynamics. He proposed that black hole entropy is proportional to horizon area in units of the Planck area, specifically S equals K times A divided by 4 times the Planck area squared, where A is the horizon area and the Planck length is approximately 1.6 times 10 to the negative 35 meters. This is the Bekenstein-Hawking entropy formula. Stephen Hawking's 1974 calculation in Nature, confirmed by a more detailed derivation in his 1975 Communications in Mathematical Physics paper, showed that quantum effects cause black holes to emit radiation at a temperature T equals h bar times c cubed divided by 8pi times g times m times k, where m is the mass of the black hole. This Hawking temperature is determined entirely by the mass of the hole, inversely proportional to it. A solar mass black hole has a Hawking temperature of approximately 60 billionths of a Kelvin, while a Planck mass black hole would have a temperature of approximately 10 to the 32 Kelvin. The radiation arises because virtual particle pairs produced near the horizon can have one member captured by the hole while the other escapes to infinity. From the outside observer's perspective, the black hole radiates as a perfect blackbody at the Hawking temperature. The derivation of the Gibbons-Hawking temperature for de Sitter space follows a parallel logic. In de Sitter space, the cosmological event horizon plays a role analogous to the black hole event horizon. An observer at the center of a de Sitter space is surrounded by an event horizon at the de Sitter radius. Beyond this horizon, events are causally inaccessible. The quantum state of fields in de Sitter space, viewed from the perspective of such an observer, is a thermal state at the Gibbons-Hawking temperature. The de Sitter horizon has an entropy, given by the same Bekenstein-Hawking formula, with the area replaced by the area of the de Sitter horizon. S equals pi times L squared, divided by the Planck area squared, where L is the de Sitter radius. For our observed cosmological constant, this entropy is approximately 3 times 10 to the 122 in Boltzmann's constant units, an enormous but finite number. The finiteness of the de Sitter entropy is directly connected to the Boltzmann brain problem through the Poincaré recurrence theorem applied to quantum gravity. If de Sitter space has finite entropy, then it has a finite number of quantum microstates. A quantum system with a finite number of microstates in a thermal state will, by quantum analogues of the Poincaré recurrence theorem, return arbitrarily close to any initial state after a finite time. The Poincaré recurrence time for de Sitter space is approximately e to the s, where s is the de Sitter entropy in natural units. For our universe, this is approximately e to the 10 to the 122 in years, a number so large that the concept of waiting for it has no operational meaning, but a finite number nonetheless. Within this recurrence time, essentially every possible quantum state in the de Sitter Hilbert space will be visited, including states corresponding to Boltzmann brains, states corresponding to entire galaxies spontaneously nucleating from the vacuum, and states corresponding to the entire observable universe in any configuration you care to specify. Leonard Susskind and colleagues explored these implications in work on the de Sitter equilibrium and the causal patch picture of de Sitter thermodynamics from 2003 onward. Susskind, Witten and others noticed that the structure of de Sitter space, with its finite entropy horizon and thermal properties, resembles a system in thermal equilibrium with a finite dimensional Hilbert space. In such a system, all possible states will be visited with frequencies proportional to their Boltzmann weights, exactly as in the ergodic hypothesis of classical statistical mechanics. States corresponding to organized structures like brains appear with probability proportional to E to the negative delta S over K, where delta S is the entropy cost of the organization. States corresponding to the entire current observable universe appear with exponentially smaller probability. The implication is that the exact same statistical machinery that Boltzmann used to understand gases in the 1870s when applied to de Sitter space with its finite entropy horizon predicts that the dominant observations in the far future of our universe are not the observations of evolved beings embedded in a coherent, structured space-time. They are the observations of minimal fluctuations, Boltzmann brains, momentarily coalescing from the thermal radiation of the de Sitter horizon, experiencing nothing but thermal noise, and dissolving back into the vacuum. The universe becomes, in its far future de Sitter phase, a kind of cosmic noise generator, with coherent experience as a rare and fleeting exception. What it would mean if you are a Boltzmann brain right now. The Boltzmann brain problem is not only a concern about cosmological future statistics, it has an immediate first-person dimension that is considerably more vertiginous. If you are a Boltzmann brain, the entire structure of your apparent knowledge and experience is an illusion, not an illusion in the metaphorical sense of being incomplete or biased, but an illusion in the literal sense that it has no causal connection to any external reality. Every memory you believe you have of studying physics, reading papers, conducting experiments, or forming beliefs based on evidence is a configuration of matter that appeared by accident in a thermal bath. The question of whether you are a Boltzmann brain right now is not easily dismissed, and the criteria by which you might attempt to dismiss it are themselves potentially unreliable. Consider the phenomenology of being a Boltzmann brain, a fluctuation that constitutes a minimal conscious observer in de Sitter space would exist for a duration determined by the timescale over which the fluctuation persists before the thermal environment destroys its organization. This timescale is extremely short. A biological brain at room temperature dissipates energy at a rate of approximately 20 watts. Maintaining the brain's organization against thermal disruption requires continuous energy input from the body's metabolic processes. A Boltzmann brain, assembled in a thermal bath at 2.3 times 10 to the negative 30 Kelvin, would have no metabolic support. The organized structure of the brain would begin to disintegrate essentially immediately on human timescales, as thermal fluctuations, in this case ones that push entropy upward rather than downward, dissolve the organization that created it. This means that if you are a Boltzmann brain, your experience is extraordinarily brief. The single moment of experience you are having right now is, in the Boltzmann brain scenario, likely to be the entirety of your conscious existence. You have no past and will have no future. The memories you appear to have of yesterday, of last year, of your entire life, are not real memories. They are configurations of matter that happen to resemble the brain states that would result from such memories. The sensory data you are apparently receiving, the feeling of holding a book or sitting at a desk, the visual experience of reading these words is not the result of actual sensory organs responding to an actual external world. It is part of the fluctuation, structured to resemble sensory input by the same cosmic accident that produced the apparent memories. This conclusion is not logically impossible. It cannot be refuted by any argument that relies on the reliability of memory, the trustworthiness of sensory experience, or the validity of physical reasoning, because all of these would themselves be products of the fluctuation if you are a Boltzmann brain. The scenario is epistemically closed. No evidence that you could gather from within the scenario could distinguish it from the evolved observer scenario. The fluctuation that produced you, if it is sufficiently precise, includes a complete apparent history and a consistent apparent sensory environment. There is no internal test that could detect the inconsistency. Sean Carroll discussed this point in his 2010 book, From Eternity to Here, and in related papers, noting that the Boltzmann brain problem represents a genuine crisis for the self-consistency of scientific reasoning. Science proceeds by making observations, forming theories and testing theories against further observations. This entire process assumes that observations are causally connected to the external world in a reliable way, that the instruments we use have the properties we attribute to them, that other scientists we collaborate with are real entities with independent access to the same reality, and that the results of experiments conducted in the past actually provide evidence about how the world works. A Boltzmann brain cannot make any of these assumptions, because for a Boltzmann brain, none of these things are true. The response that most physicists make to this line of reasoning is some version of the following. We should work within the assumption that we are evolved observers embedded in a coherent world, because that assumption is the only one that allows science to function, and science clearly does function, as evidenced by its predictive success. But this response is either circular or incomplete. It is circular if you use the success of science as evidence for the reliability of the observations and reasoning that produce science, because the reliability of those observations and reasoning is exactly what is in question. It is incomplete if you treat it as a pragmatic rather than epistemic commitment, because then you are acknowledging that the cosmological theory predicts you are almost certainly a Boltzmann brain, and you are choosing to ignore this prediction on pragmatic grounds rather than on the grounds that the prediction is wrong. There is a more sophisticated response, sometimes called the Everettian or rationality defense. A Boltzmann brain would have, by hypothesis, the same prior probability for its beliefs as an evolved observer, because its apparent reasoning processes are qualitatively identical. If the prior probability that you are a Boltzmann brain is very high, because Boltzmann brains vastly outnumber evolved observers, then rational Bayesian updating would require you to assign high probability to being a Boltzmann brain, which would mean you should assign very low probability to the reliability of your observations and reasoning, which would undermine your ability to do any physics at all. Don Page explored this line of reasoning in his 2006 paper, Typicality Defended, arguing that anthropic reasoning cannot simply assume you are a typical observer without first specifying the reference class of observers, and that different reference classes give wildly different answers. The practical upshot is that if a cosmological theory predicts that Boltzmann brains dominate the observer population, that theory is in a very deep sense self-undermining. The observations that led you to adopt the theory and the reasoning you used to evaluate it would themselves be unreliable if the theory is correct. A theory that predicts its own epistemic bankruptcy is not merely inconvenient, it is arguably not a scientific theory at all, or at least not a good one. This is why many cosmologists regard the Boltzmann brain problem as more than an exotic curiosity. It is a potentially fatal defect in any cosmological model that fails to resolve it, a defect that strikes not at peripheral predictions but at the very foundations of empirical inquiry. The epistemic collapse, when physics undermines its own foundations. The deepest version of the Boltzmann brain problem is not about cosmological statistics. It is about the internal coherence of physical theorizing itself. Every physical theory is evaluated by comparing its predictions to observations. This comparison process depends on a chain of epistemic assumptions that are usually taken for granted, that measurements reflect real properties of the external world, that instruments function as their designs specify, that the laws of physics are the same everywhere and at all times, and that the reasoning faculties of the physicists conducting the tests are reliable guides to logical inference. The Boltzmann brain problem, when applied carefully, challenges every link in this chain simultaneously, and does so from within the framework of physics rather than from outside it. The philosopher-physicist David Deutsch discussed a related point in his 1997 book, The Fabric of Reality, arguing that any good scientific theory must explain the reliability of the knowledge-generating processes that produced it. A theory that explains how galaxies form while treating the telescope observations used to confirm it as brute data, without any account of why telescopes are reliable is incomplete. Similarly, a cosmological theory that predicts the thermal properties of de Sitter space without also predicting that observations conducted in de Sitter space are reliable is incomplete in a much more dangerous way. If the theory predicts that most observers in de Sitter space are Boltzmann brains who cannot make reliable observations, and if we are ourselves in de Sitter space, the theory has committed a kind of self-undermining act that is unique in the history of science. Compare this to other cases in physics, where theoretical conclusions seem to conflict with our naive picture of the world. Quantum mechanics tells us that particles do not have definite positions until they are measured, and special relativity tells us that simultaneity is not absolute. Both of these conclusions conflict with everyday intuitions, but neither of them undermines the reliability of the observations that confirmed them. An experiment testing quantum superposition does not require you to wonder whether your laboratory equipment is real or whether your experimental results are genuine. The strangeness of quantum mechanics is in the ontology, not in the epistemology. The Boltzmann brain problem is different. It introduces strangeness directly into the epistemology by questioning whether the observations themselves are reliable evidence about the world. The self-undermining character of Boltzmann brain-producing theories can be made precise using the language of Bayesian epistemology. Suppose you adopt a cosmological theory T that predicts that the probability PBB that any given observer moment is a Boltzmann brain is much greater than 0.5, say 1 minus 10 to the negative 100. Then your credence in any observation O should be updated by the factor P O given not BB times P not BB plus P O given BB times P BB. Since P BB is approximately 1, this reduces to approximately P O given BB, the probability that you would have this observation if you were a Boltzmann brain. For almost any observation, this probability is essentially unconstrained. A Boltzmann brain could have any experience whatsoever, since its apparent experiences are not causally connected to anything. The observation therefore provides essentially no evidence for or against anything. All your Bayesian updates are washed out by the prior probability of being a Boltzmann brain. This argument, formalized by Page and others, shows that a cosmological theory which assigns high probability to Boltzmann brain status is not merely philosophically uncomfortable, it is a theory that, taken seriously, prevents its adherents from doing any empirical science at all. The predictions of the theory cannot be tested because the test results cannot be trusted. The theory cannot be falsified because no observation constitutes reliable evidence. It is not that the theory is hard to test. It is that the theory, if correct, dissolves the very concept of testing. Jim Hartle and Mark Srednicki addressed this problem in a series of papers from 2007 onward, arguing that anthropic reasoning needs to be formulated more carefully to avoid these self-undermining conclusions. Their framework, which they call prediction in the universe, requires cosmological theories to specify both the dynamical laws and the initial conditions, and to make predictions that are not conditioned on the assumption that you are a typical observer in some reference class. The Boltzmann brain problem, in their view, indicates not that cosmological theories are wrong, but that the traditional way of using anthropic reasoning to extract predictions from them is flawed. The epistemic collapse threatened by Boltzmann brains is unique in scientific history. Previous challenges to the foundations of physics, from the ultraviolet catastrophe that led to quantum mechanics, to the problems with classical ether theories that led to special relativity, involve cases where the theoretical framework gave wrong numerical predictions. The Boltzmann brain problem is different. It is a case where the theoretical framework gives rise to doubts about whether predictions can be extracted and tested at all. This is why it is not merely a technical issue to be resolved by a better choice of cosmological measure. It is a fundamental question about the relationship between physical theory and empirical knowledge, one that goes to the heart of what it means to do physics. The youngness problem and anthropic reasoning gone wrong. Anthropic reasoning is the attempt to extract scientific predictions from cosmological theories by conditioning on the fact that we exist and are making observations. It is a legitimate and in some contexts unavoidable tool in cosmology where we cannot step outside the universe to observe it from a neutral vantage point. But anthropic reasoning is treacherous, and the youngness problem is one of the clearest demonstrations of how it can go catastrophically wrong. It also illuminates from a different angle why the Boltzmann brain problem is so resistant to easy resolution. The youngness problem was first identified by André Linde and Arthur Meslumian in a 1996 paper in Physical Review D, and developed further by Linde, and Meslumian in a 1994 paper. The problem arises in the context of eternal inflation and the proper time measure, one of the earliest and most natural attempts to define probabilities in an eternally inflating multiverse. In the proper time measure, you assign probabilities to different types of events by counting them at a fixed moment of cosmic proper time, then taking the limit as that time goes to infinity. The problem is that different types of bubble universes inflate and reheat at different times. A region that reheats early has been evolving for longer by the time you take your census, and has therefore had more time to produce observers. A region that reheats later is, at the time of the census, younger, and has produced fewer observers so far. But in eternal inflation, new bubbles are continuously nucleating, and most of the volume of the multiverse at any given proper time consists of regions that reheated very recently, because the inflating background is expanding exponentially and continuously spawning new bubbles. The result is that the proper time measure predicts that you should almost certainly find yourself in a very young bubble universe, one that reheated just barely long enough ago to allow observers to exist, because the number of very recently reheated bubbles vastly outnumbers the number of older ones. This prediction is in catastrophic conflict with observation. Our universe is approximately 13.8 billion years old, measured very precisely by the Planck satellite's analysis of the cosmic microwave background angular power spectrum. But the youngness problem predicts that we should be in a universe only microscopically older than the minimum age required to support observers. The discrepancy is not a factor of a few, it is a factor of roughly 10 to the 10 or more in the age of the universe, corresponding to a probability suppression of e to the negative 10 to the 10 for being in a universe as old as ours. Under the proper time measure, our very existence in a 13.8 billion year old universe is so improbable as to effectively falsify the measure. The youngness problem is instructive because it shows that not all anthropic arguments are equal, and that naive applications of observer selection can give results that are not just slightly wrong, but wildly, catastrophically wrong. The measure you use to count observers determines the predictions you extract from the theory, and the wrong measure gives absurd results. This same lesson applies to the Boltzmann brain problem. Whether Boltzmann brains dominate the observer population depends on the measure used to count them, and different measures give dramatically different answers. But the youngness problem also illustrates a deeper issue. The proper time measure was not invented capriciously. It was a natural first attempt to define probabilities in a context where no guidance existed from first principles. Its failure, revealed by the youngness problem, forced the development of alternative measures, such as the scale factor cutoff and the causal patch measure. Both of these alternatives were partly chosen because they do not suffer from the youngness problem. But choosing a measure because it avoids a specific problematic prediction is a form of fine-tuning in the theoretical framework itself, not fundamentally different from fine-tuning parameters in a Lagrangian. We do not have a deep principle that tells us which measure is correct, and until we do, the predictions of eternal inflation are sensitive to theoretical choices that are not grounded in physics. The Boltzmann brain problem lives in exactly this same space of uncertainty. Some measures suppress Boltzmann brains and some do not. Without a principled way to select the correct measure, we cannot determine whether Boltzmann brains are a genuine prediction of our cosmological theory or an artifact of an inappropriate counting scheme. This leaves the problem unresolved in a very specific sense. We know that some versions of our best cosmological models predict Boltzmann brain dominance, and we do not currently have a well-motivated physical principle that rules out those versions in favour of the ones that do not. The youngness problem also connects to the broader issue of how to handle predictions in a theory with infinitely many observers. Whenever a cosmological theory produces infinitely many observers of a given type, ratios of probabilities become ratios of infinities, which are not defined without additional structure. This is the cosmological measure problem, and it is not solved. Multiple research groups, including those of Andrei Vilenkin at Tufts University, Alan Guth at MIT, and Raphael Busso at Berkeley, have proposed competing measure prescriptions that give different and mutually incompatible predictions. The Boltzmann brain problem is one of the most sensitive tests of these measures, because different measures disagree most sharply about how to handle events in the far future of de Sitter space, which is exactly where Boltzmann brains are produced: quantum mechanics, many worlds, and the measure problem. The Everett interpretation of quantum mechanics, also called the many worlds interpretation, introduces its own version of the observer counting problem that parallels the Boltzmann brain problem in cosmology and shares many of the same technical difficulties. Understanding this parallel illuminates the depth of the counting problem and suggests that it may be more fundamental than any particular cosmological scenario. In the Everett interpretation, proposed by Hugh Everett III in his 1957 Princeton doctoral dissertation, quantum mechanics is taken to be universally valid, including for the measuring apparatus and the observer. When a quantum measurement is made on a system in a superposition of states, the universe does not randomly collapse to one outcome. Instead, it branches into multiple branches, each containing one outcome. All outcomes occur in different branches. The apparent randomness of quantum measurement results is not a fundamental feature of nature, but a consequence of the observer finding themselves in one branch among many after the measurement. The interpretation faces an immediate problem. How do probabilities arise from a deterministic branching process? If every measurement outcome occurs in some branch, and if you always end up in some branch, what does it mean to say that one outcome has a higher probability than another? This is the preferred basis problem and the probability problem of many worlds, and they remain subjects of active research. David Deutsch and David Wallace have argued in a series of papers from 1999 to 2010 that the Born rule probabilities of quantum mechanics can be derived from rational decision theory applied to an observer who knows they are in an Everett universe. The argument is technically subtle and remains contested, but it represents the most serious attempt to ground probability in the Everett framework. The connection to Boltzmann brains arises when you ask how to count observers in a many-worlds cosmology. If the universe branches at every quantum event, and if quantum events occur everywhere and continuously, the number of branches is incomprehensibly large and grows without bound. Within this vast branching structure, there are branches corresponding to evolved observers in coherent environments and branches corresponding to Boltzmann brain equivalents. Branches in which quantum fluctuations have spontaneously organized matter into a configuration resembling a conscious brain, without any causal history connecting that configuration to the apparent world the brain seems to remember. In the many worlds context, Boltzmann brain analogues arise through quantum rather than thermal fluctuations, but the logic is the same. A quantum fluctuation that spontaneously organizes a kilogram of matter into a brain-like configuration is extraordinarily improbable, in the sense that it occurs in only an exponentially tiny fraction of branches. But the total number of branches is infinite, so the total number of branches containing such a fluctuation is also infinite. The ratio of normal observer branches to Boltzmann brain branches depends on how you weight the branches, and this is precisely the many worlds analogue of the cosmological measure problem. Sean Carroll and Charles Seebens proposed a derivation of the Born rule in the Everett interpretation in a 2014 paper that relies on what they call self-locating uncertainty. Before a measurement, an observer does not know which branch they are in, and rational reasoning under this uncertainty, combined with symmetry arguments, leads to the Born rule. But this derivation, and others like it, do not directly address the observer counting problem. They tell you how to assign probabilities to your future observations, given that you exist in a particular branch, but they do not tell you what fraction of all observer moments in the wave function are coherent versus incoherent. The many worlds measure problem is formally identical to the cosmological measure problem. In both cases, you have a vast or infinite collection of observer moments, some coherent and some not, and no principled way to assign a relative weight to them without additional theoretical input. In the cosmological case, the additional input is the choice of measure over histories in eternal inflation. In the many worlds case, the additional input is the choice of how to weight branches, which is essentially equivalent to choosing the Born rule. The connection between the two problems suggests that the Boltzmann brain issue is not a peculiarity of cosmology, but a symptom of a deeper unresolved question about how to define probability in theories that produce many worlds or many observers. This connection was explored by David Deutsch in the context of the quantum multiverse and by Max Tegmark in his mathematical multiverse framework, where the question of typicality among observers becomes even more general. Why do we find ourselves in a universe with the particular physical laws and constants we observe, rather than in some other mathematical structure with different laws? The Boltzmann brain problem, viewed from this altitude, is a specific instance of the general problem of observer selection across a vast landscape of possibilities, and any satisfactory solution to one version of the problem will likely need to address the others. How cosmologists are trying to kill the Boltzmann brain. Given that the Boltzmann brain problem threatens the internal consistency of cosmological theorizing, it is not surprising that considerable effort has been devoted to finding ways out of it. These attempts fall into several broad categories, modifying the cosmological model so that the de Sitter phase is not eternal, arguing that the relevant measure of counting observers suppresses Boltzmann brains, appealing to specific properties of quantum gravity that might prevent Boltzmann brain nucleation, or arguing that the concept of a Boltzmann brain is not internally consistent. None of these approaches has achieved consensus acceptance, but each illuminates a different aspect of the problem. The most direct approach is to argue that the cosmological constant is not truly constant, but is instead a slowly decaying field called quintessence, or that the current de Sitter vacuum is metastable and will eventually decay through quantum tunneling to a vacuum with a smaller or zero cosmological constant. If the decay occurs on a timescale shorter than the Boltzmann brain recurrence time, the de Sitter phase ends before significant numbers of Boltzmann brains accumulate. The Boltzmann brain recurrence time for a minimal observer in our current de Sitter space is roughly e to the 10 to the 66 years in order of magnitude estimates, though the exact value is sensitive to assumptions about what constitutes a minimal observer and how Boltzmann brain nucleation works in semi-classical gravity. If the vacuum decay time is shorter than this, Boltzmann brains are not produced in sufficient numbers to dominate. This approach requires the vacuum decay time to be in a very specific range, long enough that the universe has lasted the 13.8 billion years we observe, but short enough to avoid Boltzmann brain dominance. This is not a fine-tuning problem in the formal sense of requiring exponentially precise cancellations between parameters, but it does require the vacuum decay time to be less than an extraordinarily large number, which is a non-trivial constraint on the landscape of vacua in any theory of quantum gravity. Raphael Busso and Ben Freivogel examined this constraint in a 2007 paper in Physical Review D, and found that it is formally satisfiable but not automatically guaranteed by any known mechanism. A second approach focuses on modifying the measure rather than the physics. If the correct measure for counting observers in eternal inflation assigns exponentially small weight to events in the far future of de Sitter space, Boltzmann brain production is suppressed regardless of the longevity of the de Sitter phase. The scale factor cutoff measure achieves this by weighting events by the expansion factor of the universe at the time they occur, which grows exponentially with time. Events deep in the de Sitter future are weighted by e to the negative alpha times t, where alpha is related to the expansion rate and t is the proper time, causing Boltzmann brain contributions to be exponentially suppressed relative to normal observer contributions. Alexander Vilenkin and collaborators have developed an alternative called the global or fat geodesic measure, described in papers from 2011 and 2012. In this measure, the universe is described by a single long geodesic, and events are counted along it. Boltzmann brains are produced along this geodesic at a rate proportional to e to the -10 to the 25 per unit time in the de Sitter phase, while normal observers were produced during the Stelliferous era at a much higher rate. Whether normal observers or Boltzmann brains dominate depends on the ratio of the lengths of these two phases. If the de Sitter phase is much longer than the Stelliferous era, Boltzmann brains eventually dominate even in this measure, though the transition occurs much later than in naive estimates. A third approach appeals to properties of quantum gravity that might prohibit Boltzmann brain nucleation entirely. Some physicists have argued that Boltzmann brains cannot actually form in de Sitter space because the quantum gravitational nature of the vacuum prevents the coherent organization of matter over the relevant scales. In a fully quantum gravitational description of de Sitter space, the semi-classical approximation that allows us to speak of particles being produced near the cosmological horizon breaks down for configurations of sufficiently high complexity. The argument is that a configuration complex enough to constitute a Boltzmann brain requires quantum correlations over scales larger than the Planck scale, and that quantum gravity effects at those scales destroy the coherence needed for the fluctuation to manifest as an organized brain. This argument is suggestive, but not conclusive, because we do not have a complete theory of quantum gravity. String theory, the most developed candidate for such a theory, has not yet provided a definitive account of de Sitter vacua. The KKLT mechanism, proposed by Kakru, Kalosh, Linde, and Trivedi in a 2003 paper in Physical Review D, describes how de Sitter vacua might be constructed in string theory from compactifications of extra dimensions, but the stability and even existence of these vacua has been contested, particularly in the context of the swampland conjectures discussed later in this script. A fourth approach denies that Boltzmann brains are internally consistent objects. This argument, developed by Kim Boddy, Sean Carroll and Jason Pollock in a 2016 paper, proceeds as follows. A Boltzmann brain is supposed to be a functioning conscious entity that forms from a random fluctuation. But for a Boltzmann brain to form, it must arise from a sequence of events in which the fluctuation coherently organizes matter into a brain-like structure. In quantum mechanics, a Boltzmann brain would correspond to a specific quantum state of the matter fields in de Sitter space. But the calculation of how often such states arise requires knowing the quantum dynamics of the full theory, including quantum gravitational effects that we do not currently understand. Without this knowledge, the rate of Boltzmann brain production cannot be calculated reliably, and arguments based on semi-classical estimates may be systematically off by factors that completely change the conclusion. None of these approaches provides a definitive resolution. The problem persists as an open challenge precisely because it sits at the intersection of quantum mechanics, general relativity, thermodynamics, and the theory of observation. And none of these disciplines, individually or in combination, currently provides enough theoretical structure to close the argument. Eternal inflation and the probability measure that breaks everything. The probability measure problem in eternal inflation is not a peripheral technical issue. It is the central unresolved problem of inflationary cosmology, and the Boltzmann brain question is among the most acute tests of any proposed solution. To appreciate why the measure problem is so difficult, it helps to understand precisely where the infinity arises and why it cannot be handled by any of the standard mathematical tools for dealing with infinite quantities. In a finite probability space, probabilities are defined by normalizing a measure over the space of possible outcomes. If you roll a fair six-sided die, the space of outcomes has 6 elements, each with equal probability, 1/6, and the probabilities sum to 1. In a countably infinite probability space, such as the integers, you can still define probability distributions as long as the sum of all probabilities converges to 1. But in eternal inflation, the space of outcomes is not merely countably infinite, it is an uncountably infinite 4-dimensional spacetime, with events at every point and every time, and no natural normalization. Specifically, eternal inflation produces an infinite number of bubble universes, each containing an infinite spatial volume. Within each bubble universe, there is an infinite amount of time stretching into the future, and within that infinite time, there are an infinite number of observer moments of both the evolved and Boltzmann brain varieties. The ratio of these infinities is not defined. Any finite number can be obtained as the ratio of 2 infinite sequences, depending on how the sequences are constructed. This is not a pathological feature of some exotic model. It is a direct consequence of combining inflation, which makes space exponentially large, with quantum mechanics, which makes the future of de Sitter space arbitrarily long. The measure prescriptions proposed to handle this infinity all introduce a regulator, a procedure for truncating the infinite spacetime at some finite value and then taking a limit. The proper time cutoff truncates at a fixed value of proper time and takes the limit as the cutoff goes to infinity. The scale factor cutoff truncates based on the logarithm of the expansion factor. The causal patch measure restricts to the observable region of a single observer. The global measure considers only events in a single long geodesic. Each of these regulators changes which events are counted and in what proportion, which is why different measures give different predictions for the relative frequency of Boltzmann brains. The scale factor cutoff measure was advocated by Alan Guth and collaborators partly because it gives sensible answers in a variety of tests, including not producing the Youngness problem and suppressing Boltzmann brain production. A detailed analysis by De Simone, Guth, Lim, Salem, and Schwartz-Perlov, published in Physical Review D in 2010, showed that under the scale factor cutoff, the expected number of Boltzmann brain observer moments is suppressed relative to normal observer moments by a factor that depends on the rate of normal observer production per unit co-moving volume. As long as at least some fraction of habitable galaxies produce intelligent observers, the scale factor cutoff predicts that normal observers dominate. But the scale factor cutoff has its own problems. It is not invariant under reparametrization of the time variable. Different choices of time coordinate give different predictions under the scale factor cutoff, which means the measure is not covariant in the sense required by general relativity. Ben Freyvogel and Marko Simonovic addressed this in a 2012 paper, showing that a covariant version of the scale factor cutoff can be constructed, but the covariant version introduces additional subtleties that make it harder to calculate predictions in specific models. The causal patch measure, developed by Raphael Busseau and collaborators in a series of papers from 2006 to 2012, restricts all probabilities to the causal patch of a single observer. Within this causal patch, de Sitter space has a finite lifetime from the perspective of any given time-like geodesic, because the cosmological horizon is a finite distance away. And the de Sitter phase eventually ends, either through vacuum decay or through the recurrence time. This naturally limits the number of Boltzmann brains that can form within the patch. However, the causal patch measure introduces a new puzzle, the census of observers depends sensitively on the starting point of the geodesic defining the causal patch. Different starting points give different observer counts, and there is no well-motivated way to average over starting points without introducing another measure. Busso and colleagues have argued that the causal patch measure is consistent with observations and does not produce Boltzmann brain dominance for reasonable parameter choices. But this conclusion relies on specific assumptions about the distribution of habitable vacui in the string landscape. The fundamental difficulty is that all measure prescriptions are, at some level, arbitrary choices. They are not derived from the dynamical laws of the theory. They are additional structures imposed on top of those laws to make predictions possible. The correct measure, if there is one, must be derived from the underlying theory of quantum gravity. And until that theory is understood well enough to yield a canonical measure, the predictions of eternal inflation remain ambiguous in exactly the regime where Boltzmann brains become important. Guth has described this situation as the measure problem, being the central obstacle to making inflation a fully predictive scientific theory. Until it is resolved, one cannot definitively say whether the standard inflationary cosmology is self-consistent in the sense of predicting that the majority of observers are ordinary evolved beings rather than Boltzmann brains. This is not a comfortable position for what is otherwise the most empirically successful model of the early universe, the Carroll-Chen model and cosmological arrows of time. One of the most ambitious attempts to address the Boltzmann brain problem while simultaneously solving the origin of the thermodynamic arrow of time is the model developed by Sean Carroll and Jennifer Chen, first described in a 2004 paper in Physical Review Letters and elaborated in subsequent work. The Carroll-Chen model proposes a radically different picture of the cosmological initial conditions, one in which our Big Bang is not a unique event, but is instead one of an infinite number of such events, arising spontaneously from a background spacetime that is itself in a state of high entropy and thermal equilibrium. The starting point is an observation about the conventional picture of the thermodynamic arrow. In standard cosmology, the low entropy of the early universe is imposed as an initial condition. The Big Bang happened in an extraordinarily special, low entropy state, and the second law of thermodynamics has been driving entropy upward ever since. But this initial condition is not explained by any dynamical law. It is simply a brute fact about our universe, accepted because it is consistent with observations and because no better explanation has been found. The canonical invocation of this brute fact is Roger Penrose's estimate in The Emperor's New Mind, published in 1989, that the probability of randomly selecting a universe with the initial entropy of ours from the space of all possible initial conditions is approximately 1 in 10 to the power of 10 to the 123, which Penrose described as an accuracy of aim that would be required of the Creator if the Big Bang state were chosen at random. Carroll and Chen argue that this picture of a special initial condition is not only unexplained, but also unnecessary. They propose instead that the universe is described by a quantum state that, on large scales and over long times, behaves as empty de Sitter space. Empty de Sitter space, with no matter or structure, is in a state of relatively high entropy for a universe of a given cosmological constant. But it is not in its maximum entropy state, because quantum fluctuations in the de Sitter vacuum can occasionally nucleate a small region of low entropy spacetime, essentially a baby Big Bang, embedded within the high entropy de Sitter background. This nucleation process does not require any special initial conditions. It occurs spontaneously through quantum processes analogous to the vacuum fluctuations in de Sitter space already discussed. Once such a baby Big Bang nucleates, it evolves according to the usual laws of physics. The nucleated region has low entropy by construction, because the nucleation process selected a specific organized quantum state. This low entropy nucleated universe will then evolve through a hot Big Bang, an inflationary phase, a matter-dominated era, a period of star and galaxy formation, a stelliferous era with biological complexity, and eventually its own de Sitter phase. During the stelliferous era, evolved observers arise. These observers are embedded in a coherent, low-entropy universe and have reliable access to the external world. Their observations are causally grounded. The arrow of time in this nucleated universe points in the direction of increasing entropy from the nucleation event. The Carroll-Chen model addresses the Boltzmann brain problem partly, but not completely. On the positive side, it provides a dynamical explanation for the low entropy initial condition of our universe. It is not a special brute fact, but a consequence of the universe having nucleated from a higher entropy background. This is a genuine explanatory advance over the conventional picture. Furthermore, in the Carroll-Chen framework, the background de Sitter space is the equilibrium state, and our Big Bang is a fluctuation away from it. This framing shifts the statistical weight away from Boltzmann brains. Within our nucleated pocket universe, the initial conditions are set such that evolved observers arise naturally during the stelliferous era, and Boltzmann brains arise only in the subsequent de Sitter phase. On the negative side, the model does not eliminate Boltzmann brains from the full picture. The background de Sitter space continues to nucleate baby Big Bangs indefinitely, producing an infinite number of pocket universes. Within each pocket universe, the de Sitter future produces Boltzmann brains. The measure problem therefore reappears in essentially the same form as in standard eternal inflation. Carroll has acknowledged this and argued that the model's main virtue is not to solve the Boltzmann brain problem entirely, but to frame it more clearly. The relevant question becomes not why our universe has low entropy, but how to count observers across an infinite sea of pocket universes, which is the measure problem in another guise. The Carroll-Chen model also makes a specific cosmological prediction. Because baby Big Bangs can nucleate at any time in the background de Sitter space, our universe has no preferred direction of time at the global level. From the perspective of the background, a nucleated pocket universe expands away from the nucleation event in both time directions, producing two arrows of time pointing in opposite directions from the nucleation point. This two-headed arrow of time is a distinctive prediction of the model that distinguishes it from standard cosmology, though it is not directly observable within a single pocket universe. The model also makes indirect predictions about the large-scale structure of space-time that might in principle be tested through observations of the cosmic microwave background. Carroll and his collaborators, including Hartle and Srednicki, have explored how the statistical properties of the CMB might differ between a Carroll-Chen nucleated universe and a conventionally inflated one. The differences are subtle and have not yet been observationally distinguished, but they represent in principle testable consequences of the model's distinctive treatment of initial conditions. The Penrose conformal cyclic cosmology as an escape route. Roger Penrose's conformal cyclic cosmology, first proposed in his 2006 paper in the AIP conference proceedings and developed at length in his 2010 book Cycles of Time, offers a different approach to the problem of the cosmological arrow of time, one that also has implications for the Boltzmann brain problem. The CCEC, as it is commonly abbreviated, proposes that the universe does not begin with a single Big Bang and end in a final de Sitter phase, but instead undergoes an infinite sequence of cycles, called eons, each of which begins with a hot Big Bang and ends with a cold, empty, expanding de Sitter phase. The key mathematical observation underlying CCC is that the asymptotic future of a de Sitter spacetime and the initial singularity of a Big Bang spacetime can be related by a conformal rescaling. Conformal geometry preserves the local causal structure of spacetime, the light cone structure, while allowing the metric to be rescaled by an arbitrary smooth function. Penrose argues that in the far future of a de Sitter spacetime, as all massive particles decay, and the universe becomes populated only by massless radiation, the concept of spatial scale becomes meaningless. Massless particles do not experience time and are not sensitive to the overall size of the space they propagate in. In this scale-free regime, the far future de Sitter universe becomes conformally equivalent to a new Big Bang initial singularity. If this conformal equivalence is taken seriously as a physical identification and not merely as a mathematical analogy, then the end of one eon seeds the beginning of the next. The conformally compressed far future of the current universe becomes the initial conditions for a new universe, which then undergoes its own hot Big Bang, inflation, stellar evolution, and eventual de Sitter phase. This new eon in turn ends conformally, seeding yet another, and the sequence continues forever in both temporal directions. The implications for the Boltzmann brain problem are potentially significant. In the CCC framework, the de Sitter phase of each eon does not persist for infinite time. It ends when the conformal crossover to the next eon occurs, which Penrose identifies with the moment at which all massive particles have decayed and only radiation remains. The timescale for this is governed by the proton decay timescale, which experimental lower bounds constrain to be longer than approximately 10 to the 34 years for specific decay modes, and by the black hole evaporation timescale, which for the largest black holes formed during the universe's lifetime is on the order of 10 to the 100 years. If the de Sitter phase of each eon ends after roughly 10 to the 100 years, and if the Boltzmann brain recurrence time is roughly EE to the 10 to the 66 years, then the eon duration is much shorter than the recurrence time, and essentially no Boltzmann brains form within any single eon. The Boltzmann brain problem would then be resolved not by suppressing the rate of Boltzmann brain formation, but by ensuring that the de Sitter phase is never long enough to allow meaningful accumulation of Boltzmann brain observer moments. This resolution is attractive, but depends critically on the timescale for the conformal crossover. Penrose's identification of the crossover with the disappearance of massive particles is not a rigorous derivation from the equations of general relativity. It is a proposal about how to interpret the conformal structure. Furthermore, the CCAC framework requires that the laws of physics in each new eon are precisely consistent with those of the previous one, which places constraints on the underlying theory that are not obviously satisfied by known physics. Penrose has also proposed a way to observationally test the CCC by looking for specific patterns in the cosmic microwave background. If the CCC is correct, massive objects such as supermassive black holes in the pre-Big Bang eon would produce concentric rings of slightly different temperature in the CMB of our eon, a signal generated by the gravitational waves emitted during black hole mergers near the end of the previous eon. Penrose, Gurzadyan, and collaborators claim to have found evidence for such rings in the WMAP data in papers published from 2010 to 2015. These claims have been contested, analyses by Vehus and Eriksson, by Moss, Scott and Zibin, and by other groups found that the claimed signal was not statistically significant above the level expected from random fluctuations in the CMB. The debate has not been fully resolved, and further tests with Planck and future CMB surveys may provide more definitive answers. Whether or not the CEC is empirically correct, it represents an important contribution to the conceptual landscape of the Boltzmann brain debate. It shows that avoiding the problem does not necessarily require modifying quantum mechanics or statistical mechanics. It can also be achieved by modifying the large-scale temporal structure of the universe in a way that prevents the de Sitter phase from persisting long enough to generate problematic numbers of Boltzmann brains. Any cosmological model that achieves this, whether through CCAC, through vacuum decay, or through some other mechanism, would remove the Boltzmann brain threat without requiring changes to the fundamental statistical reasoning that generates it: the swampland, the cosmological constant, and de Sitter instability. The swampland program, which emerged from string theory research in the early 2000s and was significantly developed from 2017 onward, provides a potentially important physical mechanism for resolving the Boltzmann brain problem. The swampland conjectures are a set of proposed constraints on which effective field theories can be consistently embedded into a theory of quantum gravity, particularly string theory. Several of these conjectures, if correct, have direct implications for the stability of de Sitter space and the long-term future of our universe. The term swampland was coined by Kumrun Vafa in a 2005 paper to describe the space of effective field theories that appear consistent at low energies but cannot be completed into a full quantum gravity theory. The complement of the swampland is the landscape, the set of effective field theories that do arise from string theory compactifications. The KKLT construction mentioned in an earlier chapter attempts to build de Sitter vacua in the landscape, but several swampland conjectures suggest that stable de Sitter vacua may not exist in any consistent theory of quantum gravity. The most directly relevant conjecture for the Boltzmann brain problem is the de Sitter conjecture proposed by Uguri, Palti, Xiu and Vafa in a 2018 paper in Physics Letters B. The conjecture states that in any consistent quantum gravity theory, the scalar potential governing the energy density of the vacuum must satisfy either of two conditions. Its gradient must be larger than a constant of order 1 in Planck units, or the minimum eigenvalue of its Hessian must be more negative than a constant of order 1 times the square of the potential. In plain terms, the conjecture says that scalar potentials in quantum gravity cannot have stable local minima with positive energy density. A stable de Sitter vacuum requires exactly such a minimum, and if the conjecture is correct, no such vacuum can exist. The implications for cosmology are immediate and radical. If de Sitter vacua do not exist in a consistent theory of quantum gravity, then the current observed acceleration of the universe cannot be due to a truly constant cosmological constant. Instead, the dark energy must be a slowly rolling scalar field called quintessence that is not in a stable minimum but is rolling down its potential towards zero or negative values. This means the universe is not asymptoting to eternal de Sitter space. Instead, the dark energy density will eventually decrease, and the universe will transition to a different cosmological phase, potentially a matter-dominated or even contracting phase, depending on the shape of the potential. If the de Sitter conjecture is correct, the Boltzmann brain problem in its standard form is dissolved. The de Sitter phase is not eternal, it is a transient episode in the universe's evolution. The Gibbons-Hawking temperature of the asymptotic spacetime would be zero if the universe evolves to a matter-dominated phase or to a big crunch, eliminating the thermal production of Boltzmann brains entirely. The Boltzmann brain recurrence time would be larger than the lifetime of the de Sitter phase, and no Boltzmann brains would accumulate. However, the de Sitter conjecture is itself contested. The KKLT construction and its variants are specifically designed to produce stable de Sitter vacua in string theory, and their proponents argue that these constructions satisfy all consistency requirements. The debate between KKLT-style landscape constructions and the swampland conjectures is one of the most active and contentious in contemporary theoretical physics. Kakru, Kim, McAllister and Zimmett published a detailed defense of KKLT in 2019, arguing that the construction is not ruled out by the swampland conjectures when the latter are applied carefully. Obiad, Uguri, Spoditneko and Vafa responded with further arguments for the conjecture. The current observational constraints on dark energy do not clearly distinguish between a cosmological constant and quintessence. The equation of state parameter W, which equals -1 for a cosmological constant and is slightly different from -1 for quintessence, has been measured by a combination of supernovae, galaxy clustering and CMB observations. The Dark Energy Survey, which ran from 2013 to 2022, constrained W to be consistent with -1 to within a few percent. The ongoing Dark Energy Spectroscopic Instrument Survey, DESI, released results in 2024, suggesting a mild preference for W slightly different from -1, consistent with a slowly evolving dark energy, though the statistical significance was insufficient for a definitive conclusion. Future surveys, including the Vera Rubin Observatory's Legacy Survey of Space and Time and the Euclid satellite, will provide significantly tighter constraints on W over the coming decade. If future observations definitively establish that the dark energy equation of state deviates from -1, this would be powerful evidence that we are not in an eternal de Sitter phase, which would address the Boltzmann brain problem at its root. The Swampland program thus represents a fascinating case where a theoretical conjecture about the structure of quantum gravity, combined with observational cosmology, might resolve a problem in the foundations of statistical mechanics and epistemology. Whether this resolution actually materializes depends on both the correctness of the conjecture and the precision of future dark energy observations. Observation selection theory and why most arguments fail. Observation selection theory, developed most systematically by Nick Bostrom in his 2002 book Anthropic Bias: Observation Selection Effects in Science and Philosophy, provides a formal framework for reasoning about your own position among a population of observers. It is directly relevant to the Boltzmann brain problem, because the core of that problem is a claim about the relative frequency of different types of observers. But applying observation selection theory carefully to the Boltzmann brain problem reveals that most of the arguments made on both sides of the debate are subtler than they initially appear, and that many commonly cited solutions are either incomplete or quietly beg the question. The central tool of observation selection theory is the self-sampling assumption, which states that you should reason as if you are a random sample from some reference class of observers. The self-sampling assumption is the formal version of the intuition that if Boltzmann brains vastly outnumber evolved observers, you should expect to be a Boltzmann brain. The crucial question is, what is the reference class? Different choices of reference class give dramatically different answers. If the reference class consists of all observer moments in the universe, including both Boltzmann brain moments and evolved observer moments, and if Boltzmann brains vastly outnumber evolved observers, then the self-sampling assumption says you should believe with high probability that you are a Boltzmann brain. This is the standard Boltzmann brain argument. But if the reference class is restricted to observers with your specific type of causal history, evolved biological organisms with genuine sensory access to a coherent external world, then by definition, you are not a Boltzmann brain, and the reference class contains only evolved observers. The second choice of reference class seems like cheating. It appears to resolve the Boltzmann brain problem by defining it away. But there is a legitimate version of this argument. Bostrom distinguishes between the self-sampling assumption and the strong self-sampling assumption. Under the strong version, the reference class includes all possible observer moments, regardless of their causal history or the coherence of their experiences. Under the weak version, only observers sufficiently similar to yourself are included. The Boltzmann brain problem bites if and only if you use the strong version. If you use the weak version, and if sufficient similarity is defined to include only causally well-grounded observers, the problem does not arise. But this resolution is not entirely satisfying. The choice of reference class under the weak self-sampling assumption is not principled. It is determined by how you define sufficient similarity, which is itself a judgment call. Different reasonable-seeming definitions give different answers. More troublingly, if the universe contains vast numbers of Boltzmann brains, each of which believes itself to be a causally well-grounded evolved observer, the weak self-sampling assumption can be applied by each Boltzmann brain to incorrectly conclude that it is not a Boltzmann brain. The argument, therefore, does not reliably distinguish genuine evolved observers from Boltzmann brains who mistakenly believe themselves to be evolved observers. A distinct approach is the self-indication assumption, proposed by Dennis Deeks and explored by Bostrom as an alternative to the self-sampling assumption. The self-indication assumption says that you should assign prior probability proportional to the number of observers in each possible world. Under this assumption, you should prefer to be in a world with more observers, because such worlds are more likely to contain an observer like you. This assumption, counterintuitively, can suppress rather than enhance the Boltzmann brain prediction. If worlds with more evolved observers have higher prior probability, and if the number of evolved observers in our world is sufficiently large, then the self-indication assumption might favor the hypothesis that you are an evolved observer over the hypothesis that you are a Boltzmann brain, even if Boltzmann brains are individually more numerous. However, the self-indication assumption has its own difficulties, most notably the presumptuous philosopher problem identified by Bostrom. The assumption implies that you should strongly prefer theories that predict larger numbers of observers, which leads to absurd conclusions in cases where two theories are otherwise equally well supported by evidence. A theory that predicts 10 to the 100 observers should be strongly preferred over an equally well-confirmed theory that predicts only 10 to the 50 observers under the self-indication assumption, which seems like a perverse way to do science. The difficulty with all these approaches is that the Boltzmann brain problem exposes a genuine incompleteness in our understanding of how to reason about observer selection in cosmological contexts. Observation selection theory provides tools for thinking about these problems, but it does not provide a unique, well-motivated answer to which reference class or which sampling assumption is correct. Until these foundational questions are resolved, arguments that purport to definitively solve the Boltzmann brain problem by appeal to observation selection theory should be treated with caution. What observation selection theory does clearly establish is the logical structure of the Boltzmann brain argument and the specific points at which competing assumptions diverge. This clarity is valuable even without a definitive resolution, because it shows exactly what would need to be established to close the argument: a principled, physically motivated definition of the reference class of observers, derived from the underlying physics rather than imposed by hand, the recurrence time and the heat death that is not final. The concept of the Poincaré recurrence time, applied to de Sitter space, reveals something that is at once deeply counterintuitive and physically precise. The heat death of the universe is not a final state, but a temporary condition. The heat death, as classically conceived since the mid-19th century, is the endpoint of the universe's thermodynamic evolution, a state of maximum entropy in which all free energy has been dissipated. All temperature gradients have been equalized, and no further work can be done. In this state, nothing happens. Time may continue to pass, but there are no events, no processes, no change. The universe is dead in the most literal physical sense. This picture is essentially correct in the short term, meaning over timescales up to roughly 10 to the 100 years. After the last stars burn out, after black holes evaporate through Hawking radiation, after protons decay, if they decay at all, and after any other irreversible process is complete, the universe approaches a state of near maximum entropy. The remaining energy is in the form of cold photons and gravitons at the Gibbons-Hawking temperature of de Sitter space, which is approximately 2.3 times 10 to the negative 30 Kelvin. This is as close to thermal equilibrium as the universe can get, while still maintaining a positive cosmological constant. But Poincaré recurrence prevents this near equilibrium state from being permanent. A quantum system with a finite dimensional Hilbert space, which de Sitter space appears to be given its finite entropy, will return arbitrarily close to any given state after the Poincaré recurrence time. For de Sitter space with entropy S of order 10 to the 122 in natural units, the Poincaré recurrence time is of order e to the 10 to the 122 years. This number is so large that writing it as a power of 10 provides essentially no intuitive grip. The number of digits in the number of digits in the number is still not a number most humans could visualize, but it is finite. After this recurrence time has elapsed, the universe will return to a state arbitrarily close to any specified initial condition, including the state of our early universe approximately 13.8 billion years ago. A new Big Bang equivalent will occur, not because the universe has undergone a phase transition or a quantum tunneling event, but simply because the random quantum evolution of the de Sitter-Hilbert space has wandered back to a low entropy configuration. This is the quantum recurrence of de Sitter space, distinct from the nucleation processes discussed in the Carroll-Chen model, but equally rooted in the finite dimensional nature of the quantum gravitational Hilbert space. The recurrence picture, if taken seriously, has a striking implication. Our current universe, with all its stars, galaxies, planets and observers, will recur an infinite number of times over the infinite future. Each recurrence is statistically independent. The universe in its de Sitter equilibrium does not remember previous cycles. But over infinite time, every possible low entropy configuration will be visited with frequency proportional to its Boltzmann weight, and configurations as complex and organized as our current observable universe, while extraordinarily rare, will occur infinitely often. This recurrence picture does not resolve the Boltzmann brain problem. If anything, it makes it more explicit. Between any two full universe recurrences, which are extraordinarily rare, there are vastly many more smaller fluctuations, fluctuations that produce a single planet, a single organism, a single brain. The ratio of full universe recurrences to brain size fluctuations is determined by the entropy difference between them. A brain fluctuation requiring entropy decrease of roughly 10 to the 25 in natural units is suppressed by E to the negative 10 to the 25. A full universe fluctuation requiring entropy decrease of roughly 10 to the 122 is suppressed by E to the negative 10 to the 122. The ratio of brain fluctuations to universe fluctuations is therefore E to the 10 to the 122 minus 10 to the 25, which is approximately E to the 10 to the 122, an astronomically large number. Boltzmann brains are not just more common than evolved observers embedded in full universes, they are incomprehensibly more common. The philosopher David Albert, in his 2000 book Time and Chance and Subsequent Papers, examined the relationship between recurrence, the thermodynamic arrow, and the past hypothesis. Albert argues that the only principled way to ground the thermodynamic arrow is to posit the past hypothesis as a brute fact about the actual universe. The early universe happened to be in a low entropy state, and this is why entropy has been increasing ever since. Albert explicitly rejects the Boltzmann fluctuation picture on the grounds that it predicts Boltzmann brains, and he argues that the past hypothesis, while unexplained, is preferable to any account that requires the observed universe to be a fluctuation. Barry Lower and David Albert developed what they call the mentaculus, a complete probability distribution over the histories of the universe, conditional on the past hypothesis, that in principle allows calculations of the probability of any physical event. The mentaculus is not a cosmological model in the usual sense. It is a framework for applying statistical mechanics to the universe as a whole, given a fixed initial condition. In the mentaculus framework, the Boltzmann brain problem does not arise in the same form, because the probability distribution is conditioned on the actual low entropy initial state of the universe rather than being derived from an assumed equilibrium background. Whether this constitutes a genuine resolution or merely a reformulation of the problem depends on whether you regard the past hypothesis itself as explanatorily adequate, which is a matter of ongoing philosophical debate. Why the problem has not been solved and why that matters. The Boltzmann brain problem has been recognized in its modern form for roughly 2 decades, since the papers of Albrecht and Sorbo in 2004, and Don Page's subsequent quantitative analyses. In that time, it has generated a substantial literature, spawned debates at major cosmology conferences, and influenced the design of several alternative cosmological models. Yet it remains unsolved, in the sense that no proposed resolution has achieved consensus acceptance, and no new physical principle has been identified that definitively closes the argument. Understanding why this is the case requires distinguishing between different senses of solution and different reasons why proposed solutions fall short. The clearest reason the problem persists is that it sits at the intersection of disciplines that are each separately incomplete. Quantum gravity, the theory needed to understand the full quantum structure of de Sitter space and to derive the correct measure for counting observers in eternal inflation, does not exist in a complete and tested form. Statistical mechanics, applied to cosmological scales and to the counting of observers, requires a solution to the reference class problem that philosophy and physics have not yet provided. The thermodynamics of de Sitter space, while better understood than quantum gravity, still lacks a complete microscopic description. The Boltzmann brain problem requires all three of these separately difficult areas to be simultaneously resolved, which is why no solution that addresses only one or two of them is fully convincing. The proposed resolutions each target a different link in the chain of reasoning that leads to Boltzmann brain dominance. Vacuum decay and the swampland conjectures target the premise that de Sitter space is eternal. If the de Sitter phase ends before the Boltzmann brain recurrence time, the problem does not arise. The scale factor cutoff and causal patch measures target the counting methodology. They propose ways of weighting observer moments such that Boltzmann brains are suppressed. The Carroll-Chen model targets the initial conditions. It attempts to explain the low entropy Big Bang without requiring Boltzmann-style fluctuations and to frame the measure problem more clearly. The CCC targets the temporal structure of the universe. It proposes that eons have finite duration, preventing infinite accumulation of Boltzmann brains. Each of these approaches addresses a real concern and makes partial progress. None is complete. Vacuum decay requires knowledge of the vacuum structure of quantum gravity that we do not have. The scale factor cutoff and causal patch measures are not derived from first principles and may be wrong. The Carroll-Chen model does not eliminate the measure problem, it reformulates it. The CCC lacks decisive observational confirmation and relies on theoretical assumptions about conformal invariance that are not established. Beyond the technical obstacles, there is a deeper reason why the Boltzmann brain problem is resistant to easy resolution. It is not merely a puzzle about the future of the universe or a technical difficulty in defining probabilities in eternal inflation. It is a challenge to the epistemological foundations of physics. Every physical theory is confirmed by comparing its predictions to observations, and this comparison process depends on the reliability of the observations. A cosmological theory that predicts the unreliability of observations is not refuted by observations. It cannot be, because observations are unreliable within the theory. This self-referential structure means that the Boltzmann brain problem cannot be resolved purely by theoretical means. It requires establishing, from within the framework of physics, that the observations we make are reliable, which is equivalent to establishing that we are not Boltzmann brains, which is equivalent to solving the problem. The physicist and philosopher Tim Maudlin has argued that the Boltzmann brain problem is a symptom of a broader disease in contemporary cosmology: the proliferation of unobservable entities, whether bubble universes in eternal inflation or branches in many worlds quantum mechanics, combined with the use of anthropic reasoning to extract predictions from these theories, generates conclusions that are internally inconsistent or empirically unverifiable. Maudlin's diagnosis is that cosmology needs to be more rigorous about the difference between mathematical structures and physical reality, and that theories which require observer counting over infinite, unobservable spacetimes should be held to a much higher standard of conceptual clarity before their predictions are taken seriously. David Albert has made a related point from the philosophy of physics side: the tendency to treat the universe as a statistical ensemble, to ask what fraction of universes are like ours, confuses the single actual universe with a hypothetical distribution over possible universes. Statistical mechanics applies to ensembles, but the universe is not an ensemble, there is only one of it. Applying ensemble-based reasoning to the universe as a whole as both the Boltzmann fluctuation picture and the measure problem in eternal inflation do, may be a category error from which many of the apparent paradoxes arise. These critiques do not resolve the Boltzmann brain problem, but they point toward what a resolution might look like. A satisfactory solution would need to derive from physical principles rather than from philosophical assumptions, a principled way to count observers that suppresses Boltzmann brains without introducing new fine-tuning. It would need to ground the thermodynamic arrow in a way that does not rely on brute force assertion of the past hypothesis. It would need to make the de Sitter phase finite, or show from quantum gravity that de Sitter space does not produce Boltzmann brains at the semi-classical rate, or derive the correct measure for eternal inflation from the underlying dynamics. These are not small asks. They correspond to some of the largest open problems in theoretical physics. The resolution, when it comes, will likely not be a minor technical fix. It will probably require a fundamental advance in quantum gravity, a principled account of how probabilities work in a universe that may contain infinitely many observers, or a physical mechanism that explicitly breaks the statistical democracy between Boltzmann brain fluctuations and evolved observers. Why the universe thinks you're a Boltzmann brain. The Boltzmann brain problem is not a curiosity at the margins of physics. It is a precise, quantitative challenge to the internal consistency of our best cosmological models, one that arises directly from combining the most successful frameworks of 20th century physics: statistical mechanics, general relativity, quantum field theory, and inflationary cosmology. The chain of reasoning is tight. A positive cosmological constant implies an asymptotic de Sitter phase. De Sitter space has a non-zero Gibbons-Hawking temperature. A space-time at non-zero temperature produces thermal fluctuations. Thermal fluctuations over sufficient time produce every possible configuration, including functioning minds. Functioning minds produced this way vastly outnumber minds produced by biological evolution. Therefore, in a universe with a positive cosmological constant that persists for sufficiently long, the overwhelming majority of observers are Boltzmann brains. And a physical theory that predicts you are almost certainly a Boltzmann brain is a theory that has undermined the epistemic foundations of the observations that confirmed it. What the Boltzmann brain problem ultimately reveals is the depth of the gap between the phenomenological success of our physical theories, their extraordinary power to predict the outcomes of experiments and to describe the structure of the universe, and their completeness as accounts of why the universe is the way it is. We can calculate the temperature of de Sitter space to many decimal places. We can map the cosmic microwave background to 1 part in a million. We can track the expansion history of the universe across billions of years of cosmic time. But we cannot yet explain, from within the framework of those same theories, why we find ourselves in the brief, improbable, structured, low-entropy sliver of cosmic history, rather than in the endless, formless thermal noise that our equations say should dominate. That gap between the world as our equations describe it and the world as we experience it is what Ludwig Boltzmann first glimpsed from the equations of statistical mechanics more than a century ago, and what continues to haunt the foundations of cosmological physics today.